What's up, YouTube? I'm about to share what I've done for a full IStructE past paper exam. So I'm going to go through section 1 and 2 of the 2025 question 4. I've personally signed up to sit the exam in 1 week. So yeah, I've done a live run through. This is partly in response to a comment I received from Trollolol3973, who, to be honest, is absolutely spitting facts. I've identified some mistakes in this, and I'm going to share those at the end. So hang around if you want to see what the mistakes are and you don't want to make them yourself. Having a look at the question, I picked up sort of like 3 key details that I think we need to articulate in our designs. So one of those is the existing sewer here that we can't load. Then the fact that we've got to design a basement, as well as this particular area that needs to be column free at level 2. So yeah, they're the sort of like 3 key details that I think we want to be capturing and illustrating in our designs. Here's the full client requirements, as well as the imposed loading, site conditions, ground conditions, and the prompts for section 1 and 2. I won't go to that in too much detail because you'll be able to read it quicker than I can describe it. Apologize for my handwriting here. So the description, this is, essentially my first attempt in live conditions. Scheme 1, I briefly say what the description is. I'm so brief, partly because my handwriting is so bad. So it's a one-way PT flat slab with band beams, piled foundation, so there's some seek and pile walls for the basement slab. Then my lateral stability, I'm using reinforced concrete shear walls. So I initially just sketched out those ground details. I think it would have been beneficial in hindsight to also just add what my allowable bearing capacities are based on the ground conditions that they give us. I've sketched out here the existing sewer. I bring my second pile walls, the invert level of the pipe to match the toe of the pile. And the purpose of that is just so I'm not actually loading, which is one of the key client requirements. And I've also maximized the depth of this slab here, which I'll show later that it cantilevers past the support here, my second pile walls. So the idea, it's not actually transferring load onto the ground, onto that second pile wall. I've got a base slab here. I decided that the piled walls didn't need to go so deep on the right-hand side versus adjacent to that existing sewer. So yeah, I started with the ground details. I think in hindsight that I would have preferred to share what I'm about to share and just like the plan sketch, because it's just a bit more readable as opposed to like going into this level of details so early. So yeah, here's in plan my scheme 1. So as I mentioned, I'm using PT band beams with one-way PT slabs and reinforced concrete shear walls. One thing that I did learn, and you can kind of see here, I started off using a pen, but I think a pencil is better because if you're like me, you'll probably make a couple of mistakes and you can just rub it out with a pencil. Pen, a little more difficult. So yeah, that's one of the key things that I think I learned. You can see here that I'm spanning 15 meters. That is probably more or less the max for PT slabs and band beams. You can see I got some pretty chunky slabs here, 375, but the benefit for that was I don't really need any transfers in that column free space on level 2 because my columns can essentially be placed on either side of that space. You can see my shear walls here. And then for the scheme, I'm pretty much just saying what my band beam details are, my column details, and my lateral stability system and the slab. So that's a view of my pretty dirty sketch there. Then I got one sketch clearly showing the vertical load path. So I'm just trying to illustrate here how my loads get into the ground. I think in hindsight, this would have been a better spot to show the ground details as opposed to just jumping into it straight away. So as I mentioned before, I'm cantilevering past the pretty much all my band beams here cantilever past, and that's key down at level 1 because I can't load this existing sewer. So I'm illustrating the vertical load path of my structure here. Then in the ground, it's essentially just a ground bearing slab, 300 thick. And I'm showing, my second pile's walls. It's where it bears onto the ground is avoiding completely that existing sewer. So that's a little sketch of the vertical load path. Then I jump into the lateral load path. So here my slabs act as diaphragms. I just, label that, have some little arrows designating the lateral loads, and it comes into my concrete shear wall. This is all really basic, but I think it's all I intend on doing to illustrate how the lateral loads get through my structure and into the ground or the foundation. So my concrete shear walls acting somewhat as a cantilever, max bending moment at the base, and that's resolved through my pile with a pile cap through some push-pull actions. I'm not doing any actual numbers here. I'm just demonstrating how the loads get to the ground. Then scheme 2. Again, brief description, partly so brief because my handwriting. So we got a steel base, a steel frame building with CLT floor plate. I'm using diaphragm walls this time for the basement. and the slabs tied into the D walls with local thickenings at column locations. My lateral stability is a steel braced frame. So here, the ground conditions, I'm showing it again. This time it's just, instead of using secant pile walls, I'm using a 600 thick diaphragm walls, where the slab is a bit thinner because it's actually tied into the D walls in this example. So I get the benefits of continuity there, but I'm also adding some thickenings at column locations. You'll see, I've got different grid spacings and different column spacings in this scheme. Little note here saying couplers at D walls. Again, I think I would have preferred to go to this sort of ground details. I think it's a bit more readable if I just start with the actual plan of my scheme 2, which is buried away down here. So scheme 2, you can see here, I'm using the minimum column spacings at 5 meter centers. So there's a little mistake here in terms of, where that column free space actually is. So I note that you can't put the columns obviously through level 2 here, but I've just said that there's a transfer at level 2. So you'll see that in the section that I'm not running those columns all the way through. You got my steel base frames at those lift shafts and voids, the CLTs just sort of spanning one direction, 5 meters max. And I note 250 UBs because that's what I just use as for span to depth to begin with. But I think when I do my calcs, I have to actually upsize them. I think that's okay because that's a pretty typical process in design. And then I've got some vertical bracing here. My scheme 1, to avoid loading that particular area of that existing sewer on the northern side of the building, my concrete PT beams were cantilevering past this point. In this scheme, I've got some diagonal bracing to pick up, diagonal vertical bracing to pick up that edge of the building and resist any, avoid loading that existing sewer. So grids here quite different. I'm using those minimum 5 meter centers. My floors are 180 CLT floor plate beams, 250 UB to begin with, columns 310 UCs, 5 meter centers. I just jot down what I estimate the transfer member will be, which is 700 WB, and I highlight that here. And the lateral stability system, I'm using 200 SHS fully welded frames. So that is my plan for scheme 2. Then here is my vertical load path. So as I mentioned before, I've got those diagonals that I'm using this time to avoid loading this existing sewer down here and not need that's my strategy there. My CLT spanning onto my beams and obviously columns, taking that down. I've got more columns in this scheme than scheme 1, so I will have a column coming down into my base slab, and I'm putting some thickenings here to account for that. I've got the bending moment going in 2 directions because if the D walls sink, the earth pressure will push up and you'll get that reverse bending moment diagram, but also when that columns, depending on the loading on that column, when that pushes down, that will also act the same way somewhat as a suspended slab where the D walls are supporting my base slab and that point load coming down is pushing in. So that's kind of why I have the 2 bending moment profiles there. And again, I'm just sketching that the D walls aren't loading that existing sewer. My diagonals are picking up here. I made a mistake with the transfer here. I kind of forgot where it was. So this is just, I guess, the benefit of doing something practice live. Like I didn't have time to sketch everything up. I think I possibly also used pen to begin with, as you can see there. So maybe it's another benefit of pencil. But I just scribbled out and just pointed, my transfer's up here. Understand that. So my lateral load path. I didn't want to design my diagonals to be in compression, so I've just noted here that they're tension only members, which is why they're not seeing any of the load. The floor is still acting as my diaphragm. Then my welded frame, you can see the diagonals here going in tension and compression. And that's essentially how the lateral loads, my lateral stability system gets through the ground. There's a local thickening in the base slab. This time it will be, in this particular instance, resisting uplift. And I've noted that here and again. It's just sort of like compression under this particular column, which actually lands at the top of the D wall. And then that load goes through the ground and then tension here. So that's the lateral load path of my second scheme. Now this here is a tool that I'm going to be using to do a scheme comparison. It's like a multi-criteria assessment. I saw it back at uni and I probably haven't even used it since, but I think it's a good way to objectively show which scheme you're going to choose. I already knew that I wanted to do scheme 2. It's better in sustainability because it's using CLT and it's got shorter spans, so that's more efficient in terms of structural material. But I did see some benefits to the scheme 1. So the way I did it, I said sustainability, I gave it the highest weighting at 50%, 25% for constructability and cost. I've just chosen this. I'm sure you can add some other things here, but sustainability is the main thing. So that should be weighted the most because I believe the question requires that. And then just a little comment here, scheme 2 has shorter spans and it uses CLT. Well, I've also got a comment here, the steel beams there's opportunity for reuse there. Then I sort of like did my score times the weighting, summed them, and I got 72.5 for scheme 1 and 65 for 72.5 for scheme 2, 65 for scheme 1, and that was just a way to objectively say, okay, one scheme performs better than the other, so proceed with that scheme. So that is how I intend to compare my two schemes and sort of objectively say why one scheme is performing better than the other. Then my client letter, I set it out a bit like an email. So it's pretty much asking you to tell you how you can remove some of the material from your scheme design. I've got some things here like move the study hall to level 4 because the higher a transfer is, the less load there is in the column, obviously, because the loads in the column pick up as you go down. So if you're going to have a transfer member, put it as high as possible. Then I've essentially said, why don't we have some columns in the study hall, because that will completely eliminate the need for a transfer. Read the sewer, I said, instead of doing all this fancy engineering to redirect the loads, how about we redirect the sewer? And I've also suggested just simply removing the basement. If you think I've missed anything here, chuck it in the comments. So section 2, I'm in Australia, so I put down all these Australian standards to begin section 2. Then I've also just listed out the critical elements that I'm going to be designing here. So I'll just briefly go through them. Won't go through in too much detail, but I've identified the CLT floor, the 250 UB steel beam, my steel column, the transfer beam, the D wall, which is required for the basement, the lift shaft, which is critical because it's my lateral stability system. And then we've also been asked to calculate embodied carbons A1 to 3, so I include that too. So when I work out my floor loads, just include, I've actually just really done like a span to depth. I'm just kind of sketching that out. I do think I need a little more homework into calcing out my CLT floor. I don't know if that's really sort of sufficient enough to justify, like in terms of like a detailed calc for section 2. I'm just briefly showing the bending moment diagram. And I also know that like with CLT floor, it's a lightweight, so vibration governs. So like I understand that. I'm not about to turn this into a science project and work out the modes of vibration, etc. in this exam, but I do note it here. Then I do steel beam calc. I'm saying it's going to be simply supported. That just, obviously makes the calc pretty easy. WS squared on out 8. And I'm also noting here, because I want to use full section capacity, I'm using the CLT to provide the full lateral restraint of my critical flange. Then do some calcs here for bending and shear to justify my steel beam. I think you see here, I started with a 250 UB, then through this process realized I actually need to upsize it to a 310 UB. I've just noted that there. I think like that's fine. That's part of design. The 310 UC column. So I really like this table, and like it actually serves a lot of purposes, because it shows, I split it between ULS and SLS because for my any like foundation checks, I'll be using allowable bearing pressures based on the conditions that they give you in the brief. But I'm comparing that against SLS loads, not ULS loads. And so that's why it's handy to, I think, include SLS loads in any like column calcs, because you get to use that a couple of times. So to actually design the column, I need the cumulative ULS load. So that's obviously Andy will require to design the column. But then as well, when I'm designing the transfer, I can use this table to look at what the axial load is at a column at a particular level. So that's sort of 3 instances where this table comes in handy. I can use it designing foundations, I can use it to design the column, and I can also use it when I'm looking at transfer members. Then, as I mentioned before, I'm using beams simply supported, so I'm not assuming they're transferring any moment. That makes this calc a little bit easier because I treat it as like just a compression member. Then I do some basic steel design, work out my effective lengths, etc., to justify that my column's okay in compression using the max axial load at the base of my column. Transfer beam, again, as I just mentioned, I picked that up from my load column rundown table on the previous slide. Then I'm just briefly drawing some, like a basic bending moment diagram for my transfer, shear force diagram, do some calcs. I think I started like, I in my concept design I had a 700 WB. You can see here, similar, I obviously might need to check some of my rule of thumbs, but I've upsized the transfer member because I need a 900 WB for bending. And I've also added here, and I think this is okay, like I don't have enough time to check everything, but I do identify that point loads, members, steel design with concentrated point loads, you want to check web crushing. So I added that as a detail in my drawings, but I didn't go through and do the actual calculation. I just added a note here saying essentially like check it later. D-wall, it's a concrete member spanning vertically. I do some rough calcs to work out the lateral earth pressure on the diaphragm wall. Again, some rough calcs to work out what that bending moment is, where that base slab is kind of like acting as a support there, where you get that peak bending moment. And then, I'm just doing some like quick calcs. This is sort of like a bit of an estimate for the bending capacity of a reinforced concrete wall. 16s at 200. You know, I think I just use that because I know what that area still is off the top of my head, which is handy, but it does sound like quite light for a 600 thick wall. May have been better to, maybe just use some heavier bars. But okay, I work out that the bars that design's okay for bending. I move on to the design of my lateral stability member. I'm just checking for wind loads here. So when I draw out my cores, I make a note that there's probably, I'm introducing a little bit of eccentricity because my center of stiffness is not in the center, which is what we want when we're designing lateral stability systems. But I don't think it's a deal breaker. So I've just added a note here, account for torsion back in the office, because I don't have, this is something we'd use ETABS for, right? So I'm using the space available. Maybe it's something that you add in your brief, or move the core to another spot so you get a more concentric lateral stability system. But anyway, I kind of noted that I'm aware of it, but I haven't done anything about it. So I've got 3 cores. I'm saying the brace frame that runs north-south are essentially going to be taking the loads together in the north-south direction. So I've worked out the tributary width of this guy here, which is 20 meters. So that means each brace frame running north-south takes a tributary width of 10 meters. Wind pressure, 1/2 rho v squared. Net pressure coefficient. I know you obviously get a wind pressure on your windward and leeward sides, but I've just combined them together quickly and called that a net pressure coefficient. So you do the calc, I get about 1 kPa. We know that kind of sounds about right for ultimate wind pressures. Then I treat it like a cantilever, where I just say max bending moment WS squared on 2 to get 864. And then from that, divided by my lever arm to get max tension and compression at the base, which is going to be my critical member for my welded frame, because the steel design, a member in compression, is going to be more critical than a member in tension. So that's how I identify the critical member here. Check that for compression, and because it passes in compression, my 200 SHS, I know that my steel frame that I've got here to account for those wind loads that we've worked out here is okay. Now doing my embodied carbon calcs, I was kind of aware that I was running out of time here, so I chose the D wall, the CLT floor, and the 310 UB. It's not everything that I've identified as my critical members, so I just added a note here saying finish your embodied carbon calcs back in the office. So probably get docked a few marks there, but I had to essentially move on to try and get within the allowable time. I've just noted where I got these embodied carbon factors from, being the embodied carbon guide from the IStructE, and also jotted any assumptions down here. That being, I'm using the international values because the values in that IStructE guide are kind of centered around the UK. So that's my embodied carbon calcs here. Check my previous video where I show how to do embodied carbon calcs if you want some more guidance there. Then in section 2, I produced 4 drawings. One thing that I think was really helpful was to actually I've got these general notes here and a legend. I'm drawing to scale. I've got a title block with some notes I buy, date. So there's some things that just make it look like a drawing. So I started with the foundation plan. You can see I've noted my thickenings at column locations. I've added a section in here. I've got my 600 thick D wall running around the walls of the basement. So there's sort of my foundation plan, and I label it. That's my first drawing. My second drawing, similar, I'm drawing a title block. I got a name, title, date. I chucked in approved, because you always see that on drawings as well, right? Then here I'm noting where I'm trying to draw as levels 1 to 4. I can't, noting that there is a bit of a difference because there is a transfer there, but you'll see that in my section, and I'm just noting it here. I've added a steel member schedule because I think that is, I see that on the drawings that we use. So again, just anything that really makes it look like a drawing, my notes here, whatnot, little box around drawing to scale, show you grids. So that's the second drawing that I'm including in section 2. Third drawing, I'm adding that section to capture by this point of the exam, I learned to use a pencil. So you can see I rub some things out. So that's something that I learned on the weekend. Here my, again, using steel member schedules where I'm labeling the columns, my diagonal bracing, showing my thickenings here, my D walls, got some general notes, and just a title block. So that's what I've got. So we're up to drawing number 3. I'm also labeling the drawings because I feel, that's a typical thing that you see on drawings, actual drawing numbers. Then my 4th and final drawing is just some typical details. So, or not typical, sorry, some critical details, I would say. So that's what it's called, it's details. So the 2 details that I picked that I thought were critical was this transfer level detail, where I've got my 900 WB picking up the 310 UC columns. So I've added some stiffeners I've added 3 stiffeners each side of the web. 2 of those stiffeners will align with the flange, one at the center here, and just, some steel detailing. And on the right-hand side, some concrete detailing. So I'm showing the couplers, how we combine the base slab into our diaphragm wall. Some other things like a hydrotite and some waterproofing, just to keep our basement waterproof. But yeah, I don't think that stuff is critical. It's just more something to make it look professional and just something I'm used to seeing. Then I really started running out of time here. It would be probably beneficial if you could add a sketch to your method statement to illustrate, it just really paints a picture of what's happening. But I did run out of time, and it wouldn't surprise me if I ran out of time again on the day, because there's a lot to get through, as I just shared here. But the method statements, I've got site establishment, install my D-walls, excavate the base slab. And I do appreciate, once you excavate to the base slab, you've got the earth pressure on one side. So I've just got a note here to add the temporary props if required. Maybe I should remove that if. So install your base slab, and etc. You can go through that. But that's my method statement, and that's essentially where I'd finish. And I just got a little note here in terms of how long it would take. So if you thought that in terms of the mistakes, I actually think I made 3 mistakes. So the first mistake that I'd say I made is, if I come back, this bracing here, I don't know if you're allowed to actually put bracing through the floor plan. Leave a comment if you think, this actually is a violation to, it doesn't specifically say don't put diagonal bracing in, but I think you're somewhat restricting access through this particular floor space when you put diagonal bracing. So I think that is a mistake that I would get docked marks for. So that's mistake number 1. The second mistake is that I ran out of time. So I think, this actually, you can't tell that here, but this took me sort of a bit longer than the time that you're essentially allocated. So I'll just have to learn what to cut or how to do things faster. If you found another mistake, feel free to chuck it in the comments, and I will get back to you. If you found this helpful, give it a like and subscribe. Thanks.